So now we've covered the problems that were in the bouncing balls review for the final. The first problem says a ball hits a wall going 10 meters per second and bounces off, going backwards at 1 meter per second. The coefficient of restitution is, well, remember that the coefficient of restitution is defined, this sort of coefficient of restitution is defined basically as the outgoing velocity over the incoming velocity. So if the incoming velocity is 10 meters per second and the outgoing velocity is 1 meter per second, then clearly the coefficient of restitution is 0.1. And the only one that matches that is this one. So let's go to the second problem. The coefficient of restitution between a ball and a surface is 0.5. If the ball bounces off the surface and is observed to travel 100 meters per second after the collision, what was the speed of the ball before the collision? So this coefficient of restitution of the ball on the surface is 0.5, which means that the outgoing velocity is 1/2 of the incoming velocity. So if after the collision it's going 100 meters per second, then before the collision it had to be going twice as much. And so the only answer really is 200 meters per second. So again, the idea is that you have a wall there, ball coming in at 200 meters per second, and then after it bounces off, it comes back at half that velocity of 100 meters per second. So if you're worried about the kinetic energy, though, since the velocity drops by a factor of 2, the actual kinetic energy would, because the kinetic energy is proportional to the velocity squared, then what that means is since the velocity drops by a factor of 2, it means the kinetic energy drops by a factor of 4. And so nearly 3/4 of the kinetic energy was lost in that collision. Last one. Consider an elastic ball that is falling downward towards the ground. The ball hits the ground and then begins traveling upwards again. At what point in the trip does the ball have the most energy stored in it as elastic potential energy? And again, the idea, what you know, is the reason why the elastic balls work so well is as they fall and they collide, the idea is that there is work done to essentially flatten out the ball. It deforms the ball. And through that compression, essentially, that work goes into building up potential energy, so that when it bounces back up again, then the ball goes upwards. And so some amount of energy lost in a collision, but the energy that's stored in the elastic potential energy comes back as kinetic energy. And so clearly the only time that really happens is not after it rebounds, it's not right before that it hits the ground, and it's not when it's moving the fastest. It moves the fastest just before it hits the ground, even before it deforms. And so at the bottom of the path, when it's not moving, right before it rebounds, and this is where the ball is deformed as much as possible. So again, the most important thing to remember for this is that the coefficient of restitution is the ratio of the outgoing velocity to the incoming velocity. It is not a measure of the loss of kinetic energy, however. So in other words, the coefficient of restitution is 0.5, then actually after the collision, because the velocity is half as much, then the kinetic energy has dropped by a factor of 4. And so this is how things actually go.